In this video, we're going to talk about applications of the dot product to the concept of work in physics. All right, so I want to begin by recalling a definition of this displacement. So the displacement, and this is something that you would have seen in calculus, and if you have taken physics, you would have seen it in physics, but definitely in calculus, you would have seen displacement. So the displacement from point P1 to point P2 can be represented with a vector. Okay, so drawing a picture, let's say that this is point P1, and then somewhere else I have point P2, and now I'm going to connect them with a vector. So from P1 to P2, so we have that vector, and I'm going to notate that as P1, P2, and then draw an arrow from P1 to P2 to indicate that's the direction of this. So the displacement represents the change in position. So in this case, the position has been changed. Maybe it started at P1, that point, and ended at P2. And we represent that change visually with this vector. So let's do an example. So let's do an example involving work. So the example is, suppose that we draw, I don't know why this says draw. I should say drag. Suppose that we drag an object 10 meters with a force of 8 newtons. At an angle of 60 degrees. How much work is done? Okay, so first off, work is a concept that's discussed in physics. If you haven't seen work before, don't worry about it. I'm going to give a brief overview of how it's computed and how it relates to the dot product. So work in physics is the amount of displacement multiplied by the magnitude of force in the direction, I'm just going to abbreviate direction, in the direction of the displacement. Okay. So drawing a picture of what's going on in this example, so we have some object. I'm just going to denote that with like a rectangle, and it is being moved 10 meters. So it's being dragged. Okay, so let's say that this vector represents that change in position, or the displacement. I'm going to indicate this, I'm going to denote it with the vector d for displacement. And then a force is pulling on this object to cause it to be dragged. Okay, and it says that that force occurs at a 60-degree angle. Okay, so that means that this angle is 60 degrees. So the angle that's given to us is the angle relative to the direction that the object is moving. So in this case, the object is moving in this horizontal direction, so the angle that they're talking about is the angle relative to this horizontal line. So that angle needs to be 60 degrees. And let's denote the force. So force is a vector as well, with F. F with this vector arrow on top of it. Okay, so the work then, in terms of these vectors, would be equal to, so the amount of displacement is what the length of this displacement vector is. So the length of the displacement vector, let's write that. So that is the length of d. And then the magnitude of the force, well, that's talking about the length of the force vector. The magnitude of the force, but that's in the direction of displacement. Okay, so what does that mean exactly? That's talking about if we were to project the force vector orthogonally or perpendicularly down, and then look at this part of it. In other words, if we were to look at that sort of projection right there, we want to know the length of that projection. Okay, so the length of that is the length of f times the cosine of this angle. And let me just call it theta to be general, but eventually we'll plug in 60 degrees there. Okay, so for the magnitude of the force in the direction of the displacement, that would be the length of f, but multiplied by cosine theta. Because we just want the length of this projection vector. That's the magnitude of the force vector, that's in the direction of the displacement. Okay, so we have length of d times length of f times cosine theta. That's a dot product. That is either, I could write it as d dot f or f dot d. The dot product doesn't matter which order you take the dot product in. If you do f dot d or d dot f, it's the same. So that is our equation for work. Let me just write that down more succinctly. Work equals force dotted with displacement. I'm going to highlight this in yellow. Oh, no, that wasn't the highlighter. Let's pick the yellow highlighter. Okay, here we go. So work is force dotted with displacement. So in our example, we get that the work is, well, we don't know like the components of either the f, the vector f, or the vector d, because we don't have axes defined. We don't know which directions the x-axis and the y-axis. So we could define those. We could define those and get components for f and d, or we know things like the magnitude of these vectors. So I can use the length of d times length of f times cosine version of the formula. So our work would be the length of f times the length of d times cosine of the angle in between. Okay, so the magnitude of the force was 8 newtons. 8 newtons. And the magnitude of the displacement was 10 meters. And then we have that multiplied by cosine, and the angle was 60 degrees. And cosine of 60 degrees, that's a nice value. That simplifies to just 1/2. Okay, so we have 8 times 10, which is 80, times 1/2, which is 40. And the units are Newton meters. And that is our work. The work is 40 Newton meters. And then fun fact about the units here, and if you've taken physics before, you might have seen this, but if not, this might be new. A Newton meter has a special name. So a Newton meter is called a joule. So in terms of our goals, we have talked about how we can apply the dot product in physics to this concept of work.